In this video, I will be explaining you the converse part of this theorem, simple approximation theorem. Okay, so here in a video, I have explained you the question and the first part of this question, and here you can see the remaining part of that video. So here converse part, you are assuming the first part in the statement, that is, now you are assuming f is measurable, and you will prove three things, that is, pi. First, this is a simple function, and the second thing what you will do, you prove is this simple function converges pointwise on e to f, and then you will prove modulus of pi n less than or equal to modulus of f, and also you will prove if f is non-negative, pi n sequence pi n is increasing. You will prove all these things. Okay, from the beginning itself I want to tell you something. This proof is, in my point of view, this proof is not proper. Okay, but we have to study it, right, to write it for the examination. So that is why I'm studying. Okay, so here you can see everything that I have told you, right? Yeah, now let you are taking a set, that is, let en is equal to set of all x belongs to E such that f of x less than or equal to n, and the value of n will be 1, 2, 3, etc. First you have to consider this set. In the statement, in the assumption we have f is measurable, right? So since f is measurable, here en will also be measurable. So that is what you are writing. Now what you are doing is you are restricting f restricted to en. We have f, right? Sequence of, what is that? Extended real valued function, right? What you are doing is you are restricting this f to en. That is what this means. F restricted to en. After restricting f to en, that is non-negative, bounded and measurable function. Okay, and then in the next line what you are doing is you are applying simple approximation lemma to f restricted to en. Okay, and you are putting in that lemma, there you can see two properties at the last, in the end of the statement. So in that two properties, in the place of epsilon, here you will substitute 1 by n. Okay, that is how you are writing. Apply simple approximation lemma to f restricted to en and let epsilon equal to 1 by n. So this is simple approximation. This you have wrote from the statement of simple approximation lemma. There exist two simple functions, that is pi n and psi n, with this property. F of x lies between pi n of x and psi n of x, and 0, this is the another property that you can see in that statement, that is 0 less than or equal to psi n of x minus pi n of x less than epsilon. Here you have choose epsilon is equal to 1 by n, so you can write epsilon equal to 1 by n. And in the next line what you are doing is you are marking it as equation number 1. Now you are subtracting pi n of x from equation number 1, that is 1 minus pi n of x. You will get this. Okay, and then keep that as it is, and then what you are doing is you are defining some other thing, that is define pi n of x equal to n. When pi n of x equal to n, if f of x greater than n, that is how you are defining. After that, therefore, from this you can say pi n is a simple function on E with pi n of x lies between 0 and f. How you have wrote here? In the above line you wrote pi n of x lies between, because f of x greater than n. So here you have defined pi n of x equal to n. When the value of pi n of x will be n, if f of x greater than n, right? So the value of f of x is greater than n, but value of pi n of x equal to n. It means pi n of x value is greater than f of x value is greater than pi n of x. That is why here you have writing 0 pi n of x lies between 0 and f for all x belongs to E. So here you have proved the first thing that you have to prove in this part, that is you have proved pi n is a simple function on E here. Okay. In the next video I will explain you the second part, that is pi n converges pointwise on E to f. Okay.